This is the second video for week 10 in EE3051B dynamic systems, and in this video we're going to analyze underdamped second order systems, and we're going to look at the overshoot of the unit step response. We're going to look at the settling time, and then we'll look at the rise time of the unit step response. And for these examples we're going to use the systems that we've been investigating starting with week 9 with the two underdamped systems. System 3, which is this system right here, and this is the unit step response, and again it has a steady state value of 1, and then system 4, which is in magenta, which was also an underdamped system. And in the previous video we looked at the natural resonant frequency, the damped resonant frequency, the damping ratio for these two systems. Let's start with a couple of terms here. Overshoot's the first term we're going to look at, and overshoot is defined as the percentage that a system goes over its peak steady state value, and the equation is y at steady state minus its peak value. We take the absolute value of that divided by a steady state value. And we multiply to convert that into percentage. We multiply that by 100%. And we see for system 4, it overshoots by 0.6, a steady state value of 1. So it's about 60% overshoot for the step response for system 4. System 3 looks to be about 0.05 or a 5% overshoot for system 3. Let's investigate further, and what we want to do is come up with an actual value or an analytical value. And the method is, and I'm not going to prove it, but the method is to take the first derivative of the unit step response, set it equal to 0 to find and solve for t, and that will tell us the time at which the peak value occurs. If we do that, we see that the peak value occurs at pi divided by omega d, which is also equal to pi divided by omega n times the square root of 1 minus the damping ratio squared. If we plug that value of t into our equation of y, or y at tp, t sub p, we obtain the peak value, and that is equal to a times 1 plus e to the minus pi zeta over the square root of 1 minus zeta squared. And that's the peak value. And if we plug that into our definition of percentage of overshoot, we can get overshoot as a percentage is equal to e to the minus pi times zeta, the damping ratio, divided by 1 minus the square root of 1 minus zeta squared, all this times 100%. And that gives us an equation. This equation can be found on page 180 in your text, and this is equation 4.36, and that's in your textbook. If we apply this to the two different systems, recall zeta for the third system was equal to 0.707. We end up with a percentage of overshoot for the third system of 4.32%, which is the actual percentage of overshoot. And just from an estimate, I originally estimated at about 5%, but it's actually 4.32%. The zeta for system 4 was equal to 0.164, and if we apply that into the equation, we compute a percentage of overshoot equal to 59.2%, and our initial estimate was about 60% of overshoot, but 59.2 is the actual value. Now let's investigate something called the settling time. The settling time is defined as the time it takes to be within plus or minus 2% of the steady state value, plus or minus 2% of the steady state value. And that's defined as the settling time, or T sub s. We can compute the settling time from the following equation, and this is also derived in your textbook. It's minus the natural log of 0.02, which is the 2%, times the square root of 1 minus the damping ratio squared, all divided by the damping ratio zeta times the natural resonant frequency, or the undamped resonant frequency. And this is equation 4.41 in the textbook, which is on page 181. Looking at the two systems again, zeta 3 was equal to 0.707, and omega natural, or the undamped resonant frequency, was equal to the square root of 18. We obtain a settling time from this equation equal to 1.42 seconds. And using the damping ratio from for the fourth system, let me clean this up, equal to 0.164, and the fourth system had a resonant frequency, natural undamped resonant frequency, equal to the square root of 37. We compute a settling time for that fourth system, its unit step response, to be within plus or minus 2% of the steady state value, is equal to 3.92 seconds. So 1.42 seconds and 3.92 seconds. So if we go about 1.42, which is right about here, we see the system is within its 2% tolerance. And for the fourth system, we have to go out a ways for that system to be within a settling time, or plus or minus 2% of its steady state. The one last characteristic of the underdamped step response is what's called the rise time. And the rise time is the time it takes to go from 10% of the steady state value to 90% of the steady state value. And we see for system 4 that time is fairly quick. Looks to be about perhaps 0.2 seconds, maybe a little longer or a little shorter. And system 3 is a little longer, to go from 10% of steady state value to 90% of steady state value. That looks to be about a half a second for system 3. Again, we can compute that time. Unfortunately, it's not a nice linear equation, and this is typically solved with polynomial fitting. And there is a subnote in the text on this one, but a pretty good estimate, if our damping ratio is between 0 and 0.9 of the rise time, is equal to 1 over omega n times 1.76 zeta cubed minus 0.417 zeta squared plus 1.039 zeta plus 1. And that's a fairly good estimate. Using our values for these two different systems, system 3 and system 4, we obtain a rise time for system 3 equal to 0.506 seconds, which by investigation of the graph, that's fairly close. And we see the rise time for system 4 using zeta equal to 0.164, and the natural resonant frequency, the square root of 37, is equal to 0.192 seconds. And so that's the analysis equations for calculating the rise time, the percentage of overshoot, and the peak value, and the settling time for an underdamped second order system.